Okay, so we said that delta PE as a magnitude is equal to delta KE. And we know that delta KE has the following equation, which is a change in kinetic energy. It is half times mass times final velocity squared minus initial velocity all of it squared. They mentioned something, so they said that it starts from rest, so V initial is equal to 0, and they want us to find V final. So we do the following. So we say that delta KE, which is 3 times 10 power 10, is equal to half multiplied by the mass, which is 1000 kilograms, multiplied by V final squared minus 0, which we don't need to plug it in. So we have 3 times 10 power 10 is equal to 500 times V final squared. So V final squared is equal to 3 times 10 power 10 divided by 500, since the 500 is multiplied by V final squared and not the 3 times 10 power 10. This is why we divide by 500. So we can get the value of V final squared, but they want us to find V final. So how do we find V final? We just use square root for both sides. So at the end we will get that V final is equal to square root of 3 times 10 power 10 over 500, which is equal to around 7.7 times 10 power 3 meters per second. This is the magnitude of the speed of the final velocity. Next thing that we have, which is the point charges. Now for potential of point charges we have a different formula. So this is a point charge, which is Q. This is any point P that we need to find electric potential on, and they are separated by a distance of R. So we say that voltage at point P is equal to the following. It is K times Q over R. Here we take the sign of Q, since it's a scalar, and we need to check whether that point it has higher potential or lower potential. So in this example we will do the following. So let's call each charge by a name. So let's call this one as Q1, let's call this one as Q2, and let's call this one as Q3. So to find voltage at point P, we just need to find V1 and add it to V2, and then we add it to V3. Simple as 1, 2, 3. So we say that Vp is equal to K Q1 over, what's the distance from Q1 to point P, which is 0.35, since it is a rectangle. 0.35 plus V2, which is K times Q2 over, what's the distance now from Q2 to point P, which is this distance. Let's call it as X. So how do we calculate X? Simply we have 0.35 over here, and we have here 0.2 meters, so it would be equal to radical 0.35 squared plus 0.2 squared, which is equal to 0.403. So plus the last one, which is K Q3 over the distance, which is 0.2. Alhamdulillah. So simply we plug in the values. So we have 9 times 10 power 9 multiplied by Q1, which is minus 8 times 10 power minus 6 over 0.35 plus 9 times 10 power 9 multiplied by Q2, which is Q1 here is positive, so it's plus 8, multiplied by Q2, which is 1 minute, this is 0.2, okay, 0.35, okay, multiplied by minus 12 times 10 power minus 6, all of it divided by x that we calculated, which is 0.403, plus the last one, plus 9 times 10 power 9 multiplied by minus 8 times 10 power minus 6 over the distance between them, which is 0.2. And when we calculate all of it, we will get that it is equal to around minus 4.2 times 10 power 5 volts. On the calculator, you won't be able to add all of them directly, so you can add the first and the second, and you take that answer and add it to the third. Or you can do another alternative, which is you can take common factor, 9 times 10 power 9, and you can do it like this. Take the 9 times 10 power 9 as a common factor, and then you multiply it by Q over R for each one of them. So first one, which is 8 times 10 power minus 6 over 0.35 plus minus 12 times 10 power minus 6 over 0.403 plus minus 8 times 10 power minus 6 over 0.2. When you do that, you will get the same answer. We just took the K as a common factor. Last topic in this lesson, which is the equilibrium position. Okay, so I'll do this example. In potential, we have two equilibrium positions. One of them is inside, one of them is outside, and we need to find both of them. The position for that equilibrium position is always also closer to the smaller magnitude. So here we're saying that Q1, which is 5e, Q2 is given as minus 15e. So we need to find two equilibrium positions. They're separated by a distance of d, here is given as 24 centimeters. So we need to find an equilibrium position, one time inside and one time outside. For potential, they should always be of opposite signs in order to have equilibrium position, because it's scalar. We don't have like direction for potential. So let's start with the first position. We say that this is x, this is 24 minus x. So when you solve for equilibrium position in potential, you say the following. You say that 0 is equal to V1 plus V2, and then you plug in everything. So you say that 0 equals to K times 5e over x plus K of minus 15e over 24 minus x. So what do you do now? You just move this to the other side in order to make it positive. So this, we'll move it over here, so it would be K 15e over 24 minus x is equal to K 5e over x. What is cancelled? K and K are cancelled from both sides, E and E is cancelled. So now it becomes simple. So we have 15 over 24 minus x is equal to 5 over x. Now just cross multiply. So 15x equals to 5 times 24